on Zoom.
Okay.
We are live on YouTube and LinkedIn.
Brilliant. Let's get this started. Hello, everyone. Thank you for joining us today. My name is Kobie Crawford. I'm a developer advocate at Databricks, and I'm joined by my colleague Dan Liden, also a developer advocate focusing on AI at Databricks, and by our esteemed guest, Akshita Bhagia from AI2. She's going to be telling us about OLMo. She's a research scientist at AI2 right now and is the senior research scientist that has been giving us a lot of the latest updates about their 7 billion parameter model release recently. And with that little bit of introduction, let me hand it over to Akshita and get us started. Thank you for joining us.
Yeah, thank you for having me. I'm just going to share my screen. I hope you're seeing my screen.
Yes, looks good.
Okay, great. Yeah, so my name is Akshita. Hello, everyone. And I'm a senior research engineer on the Allen NLP team at the Allen Institute for AI, or AI2. And I'm here to talk about OLMo. For those of you who are not familiar with AI2, it's a nonprofit research organization. It was founded by Paul Allen in 2014. And our mission is to contribute to common good by doing high-impact research and engineering projects for AI. And one of our key focuses for the last year or so has been the OLMo project. So OLMo stands for Open Language Model, and it is our effort to develop language models scientifically and collaboratively. Before I even talk about what all OLMo encompasses, let me actually take a step back and address the bigger question. There are already a bunch of language models out there. Why did we spend an entire year building yet another one? And how is OLMo different from all the other language models? And the answer mostly lies in the open part of open language model. There's a lot of language modeling research that's happening behind closed doors right now. We think it's important for the research community to have access to models, to open models that can be studied scientifically, and to understand their strengths and weaknesses, their biases and their risks, and to build better models collectively. And so we need models that are transparent in the modeling decisions, that can be reproduced based on the training details that are shared, and accessible for a variety of academic and non-academic audiences. We have some models that are accessible by an API, yes, but the model architecture itself is opaque. Then there are some models that have their architecture and weights public, but we don't know enough about their training details or their pre-training data. So we can't really reproduce them. So let me actually talk a little bit about how language models are actually built. There is a lot that goes into building a language model, starting from the pre-training data to how you train the model, what architecture choices you make, how you adapt your model to human preferences to make it more useful, and how you even measure whether or not a model is useful or good. So today I'm going to be talking about several projects under the umbrella of the OLMo project, belonging to each of these 4 steps. At this point, I also want to highlight some other models that have been released at varying degrees of openness. So all of these models have their model weights released. Several of them even have their pre-training data and the technical report released. We have learned a lot from these efforts, and we hope that the research community will also build on our efforts with OLMo. Okay, so what is OLMo? We want to aid the researchers in building upon our work. And in order to do this, we aim to make all of the parts of the pipeline that I just described transparent. So this is the pipeline we just saw. The data is usually the most important ingredient, and it is also usually the least talked about. Then there's the training. It's computationally very expensive. It is hard to reproduce given the lack of transparency around the nitty-gritty details. The third step is alignment. It's an important part of making models helpful in user-facing scenarios. And we need more research on this. And finally, I think we can all agree that we need better evaluation. The evaluations that we have right now, they work fine at the benchmark settings, but maybe are not as useful in the real world setting. And then as part of OLMo, we release not just the base model weights, but also the pre-training data DOLMA, the pre-training data curation toolkit, all of the intermediate checkpoints, the training code, the configurations required to reproduce our models, the training logs and reports on weights and biases, the adaptation code and data, the adapted models, and our evaluation suite and benchmarks. And with that, let's actually talk about the first step, which is data. Okay, so when we started this process, there were some open data sets out there, like C4, but we needed a larger, more diverse data set. And so we created our own. It was really important for us to release our data set alongside the models. And so the data sources that we selected were open to the public. So DOLMA is a 3 trillion token corpus, and it's built from Common Crawl, Reddit, academic papers, books, Wikipedia, and code. The data in its raw form from these sources was not really directly usable, so we also built a curation pipeline to process this data. So I'm going to talk a little bit about what this pipeline roughly looks like. The first step of this pipeline is language filtering. In this version of OLMo, we focused on English language and also code. So the first step here is to filter out documents that do not belong to English or code. We used fast texts language classifier for this. I would like to point out that no classifier is perfect. And so there is always going to be some degree of multilingual data in the corpus. But this is the best we have available. The next step is removing duplicate content. And the simplest way to do this is by removing documents that have been obtained from the same URL. So this the first step we do for deduplicating at the content level. Afterwards, we also add certain quality filters. So we don't really have a good measure of defining what we mean by quality. So we base most of our quality filters on prior work, and these are heuristics based for the most part. So for instance, we used Gopher filters. So these included having certain heuristics based thresholds on like the number of the amount of alphanumeric content in a document, and how long the document is, and so on and so forth. We also did some content filtering. We removed toxic content and also personal identifiable information. For this, we removed email addresses, IP addresses, and phone numbers. And the way we did this for every document was that for documents that had 5 or less of these PII spans, we replaced them with a generic span. So for email address, it would be just email address instead of the actual email address. And then if there were documents that contained 6 or more of these PII, then we just remove the entire document. And finally, we also deduplicate the text content beyond just URL deduping. So this has two parts. One is that we check the entire document, and if it is an exact match, then we just remove that document. We also try to do this at the paragraph level, where we define paragraph as spans separated by new line. Right. So this processing pipeline, it gives us a good data set. But since we also want to use this data to train and evaluate a model, we also take advantage of this toolkit that we have built called What's in My Big Data. It's an Elasticsearch-based toolkit that allows us to take a better look at the content of the data. And we use this to decontaminate the DOLMA dataset against the evaluation benchmarks that we are using. So here we see some common evaluation datasets, and we found that in the raw form of DOLMA, several of them were either present partially or fully in the DOLMA dataset. And on the top, you can also see the contamination results for some of the other corpora. So we remove these contaminated documents as well in order to present a more realistic evaluation results. Yeah, and this is just a comparison of our pipeline against some other known data sets. So these are closed data sets. We unfortunately don't have a lot of information about them. Hence, you see all these question marks. So a lot of them do language filtering, some of them do quality filtering, and so on and so forth. But they are at different sizes. We do have more information about the open data sets. They are smaller than DOLMA, but we know a lot more about their processing pipelines. So most of them, as you can see, do some degree of quality filtering. We also ran several data ablations to figure out a good mix of the various sources. I'll encourage folks who are interested in this to read the DOLMA technical report for more details. But one of the interesting things that we found was that it was really important to have non-web data for better performance on our evaluation. And I will discuss more about evaluation in a bit. Okay, so for the data step, here's a summary of the tools and the data set that you can use and how you may find it useful for your work. If you're interested in training models from scratch, the DOLMA dataset is a great starting point. If you're interested in understanding and created more curated versions of the data, you can take a look at the DOLMA toolkit, and you can add your own curation filters there, and also use the curation filters that we have available. If you're interested in analyzing your data and you want to decontaminate against evaluation benchmarks or any other form of decontamination, you can take a look at the What's in My Big Data toolkit. And also a bonus toolkit, which is included in DOLMA. If you're interested in using Bloom filters for deduplicating large datasets in linear time, you can take a look at the BFF toolkit. Okay, and with that, we can move on to training. Right. So the goal with this step was to produce open pre-trained language models. We share our training details in the form of our code base and the configuration used to produce the model. And we also have a technical paper upcoming that will share more findings. Just as a reminder for those of you who don't know, we released 1B and 7B versions of the model, and we have a 65B model currently training. We chose these particular model sizes primarily because a lot of prior work has also chosen these sizes, and we wanted a way to compare against prior work and to place it in the larger context. Another thing that is like a highlight for our code is that it works for both NVIDIA and AMD hardware. And the models trained on both the hardware have almost identical performance. And we thought this was really important to make the model more accessible and to make the training code base also more accessible. A little bit about the model architecture. It is a decoder-only transformer architecture. Since our goal with the first version of OLMo was to have an open modeling pipeline rather than architectural novelty. For the most part, we made architecture choices based on prior work. We did make certain departures from said prior work, which you can see highlighted here. And the thing is, the unfortunate reality is that given how expensive training is, and given the lack of details from a bunch of state-of-the-art models, every team that works on building language models, they end up having to rediscover knowledge that should ideally be shared. For example, during our initial runs, we observed a bunch of loss spikes. There were different types of spikes at different points in the training, and we used varying forms of debugging for this. But one example is that the one way we tried to debug them was to log the gradient norms and the parameter norms. And the hypothesis here was that a sharp increase in loss would correspond with a sharp increase in parameter update. So in this way, we found that in our training setting, the layer norm parameters were particularly important, and they were causing a lot of the loss spikes. Now, in the ideal scenario, we would have been able to ablate over why this is the case and figure out more details. But unfortunately, given our time and compute constraints, we went with the non-parametric layer norm. And again, here I would like to emphasize that our finding here is more like a data point in the larger scheme of things. We're not claiming that this is the best possible architecture. And it really emphasizes the fact that we need open models just so someone else can also go and figure out why certain architecture choices work better than others. Okay, there are some more other interesting findings, and again, a lot of them will be discussed in the upcoming training paper. Learning rate schedule is important. We used a linear schedule. And additionally, the following trick worked. After you're done with your base pre-training, you can further fine-tune on your pre-training data set for like about 1,000 steps. And you do that while decaying your learning rate to 0 linearly. And that kind of helps to round off the model a little bit, and it improves the performance on perplexity and downstream evaluation speeds. Again, one of those things that works, and we encourage people to try and figure out and have a theoretical, some sort of theory of why this would be. Yeah, these are just some of the downstream results. I'll talk a bit more about why you see these particular data sets in a little bit. But as you can see that OLMo is better or mostly on par with similar sized 7B models. Yeah, and here's the upward tick that I was talking about. And this is when we decay the learning rate to 0 in the last 1,000 steps. Okay, as with data, here's what you can use from the training step. If you're interested in using or fine-tuning the base models for your own use case, we have the set of 1B and 7B models available on Hugging Face and through other platforms. We also have the larger 70B model currently training, and that will be upcoming in a few months. If you're interested in training your own models or you want to reproduce our models, you can use our training code base. If you're interested in doing research on how model training, on model training progress, so these are things like token efficiency, which is how much a model learns or improves based on having seen a certain number of tokens. You can explore the weights and biases reports and the intermediate checkpoints. Okay, and now let's move on to the adaptation step. The training step gives us a base pre-trained model, but base models have several limitations. If you have played around with these base models, you may have noticed that they do have a tendency to produce repeated sequences, or they output toxic content or otherwise problematic content. And the goal for the adaptation workstream was to produce models that are better aligned with human preferences. Okay, pretend you don't see the arrows. So there are several ways to get a model to do what we want. For example, if you just have the pre-trained model, you can prompt it with in-context examples. And there are several prompt engineering techniques and hacks that people have discovered. And there are several papers on this. And that's one way to do it, but it can be quite limiting. And it is still prone to generating problematic content. So another thing you can do is instruction tuning. And the way this works is that you collect a large, diverse data set of instructions, inputs, and outputs. And then you fine-tune the base model further. So this is the supervised fine-tuning, or SFT. Of course, the problem with SFT is you're never going to be able to represent all possible scenarios. And the other problem is that you only show the model a single good output for an input. And for certain inputs, there can be multiple right outputs. And that's where human preferences and RLHF come into play. So more concretely, for aligning models, we first determine what capabilities are important for us. So for example, we wanted the model to do well on scientific tasks. We wanted it to refuse to answer problematic questions, things like how to rob a bank. Ideally, we wanted to say, I don't know, when it doesn't have information, instead of just hallucinating or making things up. And then based on these wants, we collect instruction and preference data, either with human annotation or by utilizing bigger language models to generate synthetic data. And finally, we perform SFT, supervised fine-tuning, and then optionally RLHF. There are a lot of instruction tuning datasets. Some of them are human created and some of them are generated from GPT models. A lot of models trained on these datasets, they claim to have great performance on par with proprietary models. But unfortunately, that does not give us a complete picture. So we need a systematic way to understand how useful these datasets are and how far away we are from proprietary models. So this was work done under the Tulu umbrella. And there are a couple of papers here. The first Tulu paper really introduces a more comprehensive set of evaluations needed to perform on instruction-tuned models. So this includes things like factual knowledge, reasoning, multilinguality, coding, open-ended instruction following, and safety. One of the main findings here is that different instruction tuning datasets add different capabilities to the model. So for example, training on chain of thought reasoning instruction data is particularly helpful for mathematical reasoning tasks. And so it's really best to train on a mix of different instruction tuning data. And this should be based on what your requirements are and which evaluations you prioritize. Tulu 2 goes further with publishing a good mix of instruction data, and this data and these instruction data sets include like the data sets that came after Tulu. It also releases a Llama 2 model fine-tuned on this mix. Further, under this project, we also released the largest model tuned with direct preference optimization, which is a way to train with human preferences without having to deal with RL and reward models and those finicky settings. And just to see, it performs fairly well on some of the leaderboards. So we use this Tulu recipe on the OLMo base models using the open and struct code base that was released alongside Tulu 2. And we find that instruction tuning improves performance of OLMo on the evaluation capabilities outlined in the first Tulu paper. Interestingly, it still lags behind the Tulu 2 models somewhat, which do follow the same recipe and the mix, but they are trained on the Llama 2 models. So this leaves us with several open questions on how adaptable a certain model is and how this may depend on the underlying pre-training data, which again goes back to my point, we need to know more about all of the steps in the pipeline. As with all the other steps so far, if you're interested in instruction tuning your own models, you can use OpenInstruct. If you're interested in using adapted models, we have Tulu2, we also have OLMo Instruct now. And if you're interested in figuring out what is the best mix of instruction data sets for like an overall generally good performance, you can check out the Tulu2 mix. Okay, and finally, evaluation. So throughout pre-training and for our final models, we needed a set of evaluation tasks. And that was the goal for the evaluation workstream, to have a set of evaluations to guide our training choices and to provide a report on the final modeling checkpoints. So evaluating language model is really difficult. There's no evaluation setting that's going to encompass all possible things that we would like a model to do well on. So we use both in-loop training evaluations for validating our modeling decisions, as well as offline evaluations for actually evaluating the checkpoints. And for both of these, we use a mix of downstream tasks, which are mostly formatted as rank classification tasks, as well as tasks to measure intrinsic language modeling fit using our perplexity benchmark. And so a little bit about the in-loop evaluations. So we call them online evaluations in the sense that they run alongside a training loop and are evaluated every 1,000 steps. And we use this to make decisions around model architecture or initialization or other design choices. We also have this set of core downstream evals. So these are, as I said, formulated as rank classification tasks. And the reason why we chose this particular set, it's not a very scientific answer, but unfortunately, these are the data sets that we observed as giving us more signal. These are the ones that changed most based on the different architecture choices that we made. I'm also going to talk a little bit about the perplexity benchmark. So evaluating on downstream tasks and benchmarks, it gives us a sense of how the model is performing on that task. But these tasks are framed in a very specific way. So for example, rank classification or coding tasks. And that's useful, but we also want to have some measure of how the model is doing intrinsically on language modeling itself. So how well it is able to model the distribution of the data. So perplexity is commonly used to measure distributional fit, but measuring perplexity on a monolithic held out data can be a very crude measurement of language modeling ability. So what does it even mean if you say that your model reduces perplexity on all of C4? So Paloma is a benchmark for assessing language model fit in a more fine-grained way. So it measures perplexity for 585 text domains, and these are collected from 18 different sources like C4. And one of the important use cases here is for practitioners who are not actually interested in building language models, but say they want to figure out which language model to use for their own specific use case. So say, for example, if you're a medical practitioner and you are trying to figure out if a particular model is right for you, you can create a specific task that measures, and you can formulate it in a very specific way, but that can be time consuming and expensive. So instead of creating a specific downstream task, you can as a first step, evaluate the perplexity of the language model on just medical literature domain. And this has a much lower threshold to get started on, because you just need to give it raw text. Again, the summary. If you are interested in running our evaluation suite, reproduce our numbers or reproduce numbers on some of the other language models, you can use our evaluation code base. And this is built primarily on Catwalk, which is a library that we have. And again, if you're interested in assessing which language model to use for your specific use case, I encourage you to check out OLMo. Okay, OLMo is a big project. It wouldn't have been possible without the support of all of our partners. We were very fortunate to have compute from AMD and Lumi, from the Kempner Institute at Harvard, and of course from Databricks. We also partnered with UW, with DSRI, and with Surge and Together AI, and they were helpful for various stages in training and adaptation. Here are some quick links for those of you who just want to get started right away. And thank you. With that, I guess we can take some questions.
Fantastic. Akshita, thank you very much for the presentation. We do have some questions. What we've prepared in advance in terms of some of our questions across from our own team, we're going to transition to in a moment, but right now I'm going to relay some of the questions that came in through the chat from our panel, from our audience. So let me start at the top. There was a question here about how we define toxic content in the data set.
Yeah, so this is very much open to interpretation, and different people have their own interpretations. There are some general guidelines. So for example, the example that I gave was how to rob a bank, how to build a bomb. These are things that are very obviously things that we don't want the model to generate or talk about. So there are these general guidelines, and then there would be some specific guidelines based on maybe cultural scenarios, and they would be applicable differently based on what your use case is.
Right on. Makes sense. Very cool. Thank you. And then the next question that we have here is sort of a clarifying question about data contamination. And basically, what exactly does that mean? I think, like, as you described in your talk, I think that's actually relatively better answered at this point, but just for any final clarification to make about contamination.
Sure. So the general idea behind contamination is that when you're evaluating models on your evaluation benchmarks, it's important that that's actually unseen tasks, unseen data. Because if your model has already seen that, then you will be overestimating how good your model is. And the problem, like when NLP was like a younger field, we used to build these custom evaluation data sets and custom training data. Now, of course, we get all of CommonCrawl and we get all of the internet. And so it's really difficult to see whether your particular evaluation benchmark is part of that. It's hard to pinpoint at an exact date document in your data and say that's contaminated, because the size of the data set is just too large to make that feasible. And so the What's in My Big Data toolkit provides a way to do that in a somewhat feasible manner. And decontamination is then just you detect that your evaluation benchmark is present in your data set, and then you just remove those documents.
Yeah, makes perfect sense. All right, excellent. Thank you. All right, the next question was about clarifying the additional 1,000 steps. What is the data used for the additional 1,000 steps, and what was the starting learning rate for that phase?
Yeah, so it's just more of the pre-training data.
Okay.
I mean,
And then
there are open questions on what other data you could use. We use the pre-training data. We did some ablations. But yeah, it's that's what we use, but we encourage you to try out other things.
right on. And then did you have a specific note about what the starting learning rate was? You know, when people took a note of the fact that the decaying the learning rate to zero during that process was something that
Yeah. I don't remember off the top of my head, but I encourage people to check out the weights and biases report to see what the starting point was.
right on. Makes perfect sense. All right. And then there were some questions, obviously a lot of them about the data. So I've got a couple more here.
Okay.
The were there any specific tools or techniques that you used to decide what part of the data set was for pre-training versus fine-tuning? Was there anything that you did to define?
We sampled it and we had a held out data set. We did some decontamination, especially for things that we knew we were going to evaluate on. So things like Paloma.
Okay, fantastic. Yeah, and Paloma is really, I think it's a really promising area for seeing like what you've offered in terms of how you opening that up, and then what people are going to do with it from here. I think it's going to be really interesting to watch. There were questions about about during the training process, loss spikes. How often did you encounter loss spikes? And what were your techniques for managing that?
Yeah, so it's the strange part is that one of the things that we found was that initialization plays a huge role. So for example, we were looking at our initial training run and we were observing this really fast loss spikes. And we figured it might be something in the data. And I will share what the problem with the data was in just a second. But we also started another run from scratch with a different initialization, and we found that that didn't have loss spikes. So there are things that you can do to debug it. Unfortunately, there is not enough research. There is a lot more scope for doing the kind of research that we have so far. So a couple of interesting things with the data. So for these particular loss spikes, the problem was that the data contained long sequences of just the word M, and we trace this down to Reddit, which has something called the microwave gang subreddit, and the entire purpose is that everybody posts just long sequences of M followed by ding. And somehow that got through our curation filters, and that was causing the loss spikes. There are a lot of other fun, interesting things with the data. So, for example, in the initial runs that we were doing, so at that point, OLMo was not ready, but we were doing some trial runs on just C4. And we observed this really interesting thing is that the performance on the downstream evaluations was quite fine. But then on the perplexity, we were observing this weird jump in perplexity just for the pile data set. And it was very strange. And ultimately, we narrowed it down to the fact that C4, because of the way it is filtered and curated, it never sees two new lines in the same in the same sequence. And so Pile obviously had data where there were multiple new lines in a row. And so if you just train your model on C4 and it has never seen new lines two in a row, then your perplexity on Pile is going to increase. So yeah, there are these like tiny little things and nitty-gritty details that just are really hard to all document and keep track of.
Yeah, that sounds really interesting. Just more new lines. Wow. So let me hand over to Dan. He had some additional questions that we wanted to get into. We're going to see how many we can get through across the ones that have all come in from the audience and stuff like that. But Dan, do you want to pop in some of these questions?
Absolutely. So first of all, thank you, Akshita, for the presentation. That was great and really emphasized how openness encapsulates so much more than just the model or the model weights. Taking a quick break from the training details and be interested in a little bit of background about you and your history with AI2. What is special about AI2 as an organization, and what drew you to working there, given your experience and interests?
Yeah, sure. I started at AI2 in 2020, and this was right after my master's degree. Um, so before my master's degree, I had worked as a research programmer at a company called Infocusp. And they did a lot of cool projects in the ML space. And I was working on a particular project around creating a data science platform for building financial data sets and models. So this was kind of work at the periphery of machine learning. And so that's where I got interested in machine learning. And then because I have this interest in books and in computers, I felt like natural language processing was the perfect fit. And so that's where I decided to pursue a master's degree. And I chose to go to universities with good NLP professors. Um, I've worked on a bunch of different research projects and class projects in NLP during my master's. And then AI2 specifically, the reason why I was attracted was that it was a research organization, it was nonprofit. Um, and it had this great emphasis on doing high impact work with us with a fairly compact team. And it wasn't like you're doing research and it's getting published and then that's the end of that. The focus really was on a lot of impact. And that was really attractive to me. Um, so when I first started at AI2, I'm on the ALN-NLP team. And some of you may know that that team was built around the original ALN-NLP library. And this was back when transformers were not like as mainstream. And so people experimented with different architectures and different models for their NLP models. And the NLP library was a way to experiment that in a more modular way. So that's just an example of the kind of work that we wanted to do, which was to enable other researchers to build upon our work and to build on using best practices and best engineering practices. And that is what kind of got me attracted to AI2.
Great. Sounds like a very good fit. You talked about impact being really important, and I know one of your early slides talked about the focus on the common good. Can you talk a little bit about how this idea of openness and the focus on open models contributes to some notion of the common good?
Yeah. So I think openness is really important right now. We have all these companies working on language models, and these are really powerful models. And they are shielded by APIs, and we know nothing about their architecture or what data sets they were used to train on. And so we have these very small set of companies making decisions uh, on what is turning out to be a really powerful, ubiquitous technology. And they are the ones who make decisions on even figuring out like what things are considered toxic by the model, or what things are okay to talk about, what things are not okay to talk about. If there are jailbreaking attempts, they are the only ones handling it, and we don't have other researchers potentially contributing to make those models safer. And so for all of these reasons, I think it's very important to have open models, just so that the research community as a whole can make an impact on every single step of the entire pipeline of building language models.
Yeah, that makes a lot of sense. Are there any specific use cases or research questions you were hoping to address given the choice of what assets to make open? I know you mentioned the model weights and checkpoints, data, evals, logs, adaptation code, or was the goal more broadly just to be as open as you possibly could be?
Yeah, so as the first step, our goal was to just open up the entire pipeline, just so it even invites more research questions that can be asked about it. So you mentioned checkpoints, and there are so many things you can do with figuring out um, how a model progresses in its training, and ask a lot of research questions there. There are things like token efficiency in training models. So if you have two models and they have seen the same number of tokens in their training run so far, and one of them is better than the other, what does that mean? Is it something to do with the data? Is it something to do with the architecture? And so by even opening up the pipeline, you're enabling researchers to start asking new questions. And so there was this dual purpose. We wanted to open up, we had certain questions in mind, and we really wanted to enable researchers to have even more questions.
I love that, creating the space to ask questions that you couldn't have even asked before under different
Exactly.
frameworks. That's very interesting. So if I'm a company or a researcher and I'm at a phase of a project where I'm choosing a model, why might I choose Almo 7B, for example, over another 7 billion parameter model that performs comparably on the benchmarks? Like, what are the sort of tangible benefits to researchers or companies of choosing, again, like comparably performing models, but with these differences in what assets surrounding it you have available?
Right. Yeah, so there are several ways to think about this. If you are a researcher interested in building language models or understanding the modeling choices, of course, I highlighted the way in which these tools can be useful to even provide comparisons at an earlier stage of modeling. And even as a practitioner, it's helpful to go beyond the benchmarks to evaluate the model for your task-specific needs. And the eval tools that we release provide a way to do this. If you should ideally even look at your training data or look at the data that your model is trained on to make decisions on whether or not that model is right for your case. The What's in My Big Data toolkit gives you a way to do that. And of course, if you're using Dolma, we have ample documentation available. In most cases, if you're trying to use the model, you're not going to use it as is. In most cases, you're going to fine tune further. We have the training scripts available for doing that, and you can use them directly. And finally, there's a license, which for the OLMo 7V model is Apache 2. So that ought to give practitioners some more degree of freedom around how they want to use the model.
Got it. That makes sense. So a lot of freedom to do what you want and a lot of confidence that you can pull back the curtains on any part of it and really understand how it got to where it is.
Exactly.
One last question on the topic of openness. So AI2's projects, many of them are open source. Can you tell us a little bit about how AI2 invites participation from the community with its open source projects, and if anybody listening is interested in getting involved, how might they take the first steps to do that?
Yeah, so AI2 has a long history of having open source projects that are built for the community and that the community participates in actively. So one of the primary examples of this is the original LLNP library. We have sunset that since the world moved to transformers, and the underlying principle of having open tools that other researchers and other practitioners can contribute to remains. So if you want to get started, we have the OLMo library open source, and you can get started there. For all of the stages of our pipeline, yes, there are a lot of libraries that are documentational, but then we also have most of the libraries you can build so much more on top of that. So you have the OpenInstruct library, you have the Dolma set of curation filters, and we really encourage people to play around with these libraries, to use them, and hopefully the goal is that we'll be able to build better models more collaboratively.
Great, that's great. Such a huge surface area to contribute to.
Yeah.
Couple of questions about the model itself.
Okay.
So much of the emphasis of the coverage and discussion of Almo, including much of our discussion so far, has been focused on the openness of the project. Rightly, I think that's such a huge innovation in the space. But I'd love to hear a little bit more about the models themselves, if there are any specific details that you think people maybe miss when focused so much on the openness or in innovations in the model architectures that you'd like to call out.
Yeah, so again, I discussed this a little bit in my presentation. The goal with this version of OLMo was really to open up the pipeline. And so for the most part, we went with like safe architecture choices, things that we knew were likely to work well, given our time constraints. And then we did make some departures from those default choices. So things that are discussed like the non-parametric layer norm. There were some other things around wait time not being particularly stable for our use case at the 7B level. And so a bunch of such details and such design decisions are outlined in the training paper that we have upcoming. And I'll encourage people to go and read that when it's out.
On the topic of training, I had a question sort of informed by, a lot of my previous background was in training more classical ML models or much smaller models. And obviously this super large scale training is different. The Almo paper mentioned that training hyperparameters were chosen by optimizing for training throughput on our hardware while minimizing the risk of loss spikes and slow divergence. Can you expand a little bit on what this means, how it might differ optimizing for training throughput rather than just optimizing to get the smallest loss possible on a smaller model?
Yeah, so I think given the size of these models and given the amount of data that we want to train on, it's kind of hard to ablate on all possible choices and like figure out the best set of hyperparameters that is going to give us the best loss. Yes, that's our main goal, obviously. But we are also constrained by the training data that the training hardware that we have. It's very expensive to run these models. It's impossible to ablate for all different hyperparameters. And so we really had the goal that whatever training hardware that we have available, we are maximizing that. And we are making sure that the model is seeing as many tokens as possible. And the idea here, the hypothesis here was that the model seeing more number of training tokens is going to be much more impactful than any of the architectural tweaks that we might be able to make. This may or may not be true. This is the choice that we made given our constraints. And we hope that other people will be able to update more specifically on particular design choices, given that now we have all these tools available.
Got it. That makes sense. So sort of optimizing toward making sure the model can see as many tokens as possible as a huge priority. Exactly. That makes sense. On the topic of hardware, another detail I found interesting in the paper was the training the same model on two different kinds of hardware to generate the Almo 7B twin model. Can you talk a little bit more about the motivation behind doing that and what you hope to learn from it?
Yeah, so again, one of the emphasis that we had was on accessibility. Of course, if we are able to train the model on different types of architecture, of hardware architectures that we have available, that's a lot better for making these models accessible and also making the training pipeline accessible. So that was one of the motivations. We also were motivated by the fact that these were the hardware that were available to us. And so we were really motivated to get them to work on all the hardwares that we had available. There were a lot of interesting things that happened with AMD hardware. It is we know that NVIDIA has a very strong software surrounding the hardware. AMD is maybe not quite there yet, and so we ran into some issues around specific implementations. But the great thing was that we were able to solve for some of these bugs. For example, we had an issue with the layer norm not working quite as expected. So we have fixed that now. It works well. So there were a lot of different stories that were part of what happens when you train with AMD hardware. And we will discuss some of those again in the upcoming training paper.
If you don't mind me in right now, two things. We're down to about 5 minutes left before the top of the hour. But as you mentioned hardware, one of the things that I thought really worth mentioning is one of the reasons why we as Databricks are getting involved in wanting to help AI2, get the word out about OLMo and whatnot is partly because as one of those partners that you mentioned in your presentation, we worked to provide some of the capacity that the AI2 used to train these models.
Yeah.
And and one of the things I just wanted to mention in terms of like how well that relationship has gone is that Databricks and AI2 have been we've been friendly for quite some time, and the team that was Mosaic ML was working with the folks at AI2. I joined Mosaic ML in 2021, and the connections and communications that were going on, and the sharing of technical information and sort of collaboration across our organizations has been going on since the time I joined the company. It's been wonderful, a wonderful partnership and a relationship overall. And so, we've been happy to help by providing some of the capacity that's been used, and funnily enough, some of when the AI2 team has been working with the capacity we have, it's been one of those things where they've been really, really good at, here's the capacity, here's the interface for getting started, and then running off and doing everything that needed to be done. And the technical savvy and depth that the AI2 team has demonstrated has been one of the things that's made it both really useful for us as learnings for the platform. Some of the things that you've done in terms of like feedback on our training libraries and our training interface, as well as just the way that you've been able to use it and actually get great things done with it. We just wanted to say thank you for the great collaboration and partnership. It's been a wonderful thing across data sets, across the actual training regimen, all of these bits. So wanted to say thank you and make sure that people understood how well the Allen Institute has been doing. One of the ways that Jonathan Frankel talked about it is that AI2 is punching way above their weight in terms of the ability to deliver great AI research and actually having these kinds of both the data sets, the code, the training methodology, sharing all these results. That they're doing really amazing work, especially in this space where it is so resource intensive to get any of these things done. So thank you for doing that with us and for making that happen.
Yeah, absolutely. And it's been great collaborating with Databricks as well. Everybody, please work with Databricks.
Yeah, right on. So as we get close to the end, Dan, do you have maybe one last question, or Akshita, do you have one particular share that you'd like to sort of close us out with?
Yeah, I think the space is in a really, the field is in a really interesting space. We need more researchers, we need more people to get involved. And we hope that you find our efforts with OLMo useful in your efforts to get involved in this field.
Fantastic. Right here, there's a lot to be said in terms of finding the resources. We've been sharing back in chat the links that you shared in the slide deck. We will be getting the video recordings out and available for everyone on YouTube in a variety of forms. We'll have some shorts clipped out of this and stuff to capture specific moments, but also make sure that have that just the full long form discussion available. Keep an eye out also for continued chat and questions and answers happening over on Twitter, on X. And make sure that if you do have follow-up questions, reach out to Allen AI at Allen_AI online. You can follow up with us at Databricks, and we'll also make sure to share our personal handles so that you have a way to reach out to us both on X and LinkedIn. Thank you again very much for making this webinar happen. Really great to be here for it.
Thank you so much for having me.
Thank you.
All right.